Let's take up physical properties. Nearly all transition metals display typical metallic properties just as high tensile strength, ductility, most of them are malleable and ductile, most of them have high thermal and electrical conductivity, they have metallic lustre. Exceptions are zinc, cadmium, mercury and manganese, which have one or more typical metallic structure at normal temperature. These are their crystal structures. Scandium, titanium, vanadium, chromium all have BCC structure. Scandium can have BCC as well as HCP. Titanium have HCP and BCC. Vanadium only has BCC. Chromium has BCC and CCP structure. Manganese has got normal metallic structure, which is denoted by X. It can have HCP structure also. Iron has BCC and HCP structure, cobalt CCP. CCP means cubic closed packing, PCC means body centered packing, X means normal metallic structure. Nickel also is CCP, copper is CCP, zinc has normal metallic structure or typical metallic structure, it can have HCP. Yttrium has HCP and BCC, zirconium HCP and BCC, niobium BCC, molybdenum BCC, technetium HCP, ruthenium HCP, rhodium, palladium and silver have CCP and cadmium has typical metallic structure. It can also have HCP structure. Lanthanum HCP, CCP and BCC, hafnium HCP, BCC, tantalum BCC, tungsten BCC, rhenium HCP, osmium HCP, iridium CCP, platinum CCP, gold CCP, and mercury has normal metallic structure. It is liquid. BCC stands for body centered cubic, HCP is hexagonal closed packing, CCP is cubic closed packing, and X is typical metal structure. Next, we are taking trends in melting point of transition metals. In the first transition series, we will find chromium has highest melting point. Reason is it has highest number of unpaired electrons. Therefore, it can form d pi bond, which is responsible for strong forces of attraction between the atoms. That is the reason it has high melting point. Manganese should have highest melting point, but it has typical metallic broken crystal lattice, due to which it has lowest or low melting point. Zinc, cadmium, mercury. Zinc has got low melting point because zinc, cadmium, mercury, all the three have low melting and boiling point. Reason being that they have all the d orbitals full and only 2 electrons in valence shell s orbital. That's why they have weak metallic bonding. That's why they are high volatility. So the transition metals have low volatility except zinc, cadmium, mercury, which have high volatility. Their melting and boiling points, transition metals have high melting and boiling points except zinc, cadmium, mercury, which have low melting and boiling point. They have high enthalpy of atomization. Here we will find molybdenum has highest melting point because of large number of unpaired electrons. In the third transition series, tungsten has highest melting point due to large number of unpaired electrons. So the maximum at about middle of the each series indicate that one unpaired electron per d orbital is particularly favorable for strong interatomic force of attraction, or we can say greater the number of unpaired electrons, more will be d pi bonds and stronger will be metallic bond. This is the heat of enthalpy of atomization of transition metals, and series 1, series 2 and series 3, and if you observe it has irregular trend. First it increases, then it decreases, then it goes on increasing. Similar trend are followed in all the 3 series. So these are trends in enthalpy of atomization of transition metals. They have high enthalpy of atomization due to strong metallic bond, and strong metallic bond is due to their smaller size and more number of valence electrons, and unpaired electrons are also responsible for d pi bond, which leads to high enthalpy of atomization. In general, ions of same charge in the given series progressive decrease in radius with the increase in atomic number. Now electron enters a d orbital each time the nuclear charge increases by unity. It may be recalled that shielding effect of d electron is not so effective, therefore effective nuclear charge increases and ionic radius decreases. The filling of 4f and 5D results in regular decrease in atomic radii called lanthanoid contraction, which essentially compensate for expected increase in atomic size and increasing atomic number. The net result of lanthanoid contraction is that the second and third transition series have almost similar radii. Zirconium resembles with hafnium, niobium resembles with tantalum. They have similar physical and chemical properties which are much more than the expected. Trends in atomic radii. These are the trends in atomic radii. When we move from scandium to zinc, first they goes on decreasing, and in the middle with iron, cobalt, nickel, they almost remain the same, and then in copper and zinc they go on increasing. The reason is that first effective nuclear charge decreases. Why? Because unpaired electron increases and therefore effective nuclear charge increases. But in case of copper and zinc, the size is slightly more because we have got filled d orbital. Here we have 3d10 full and here also 4s2 3d10. That's why effective nuclear charge becomes less and their size becomes more. Similar trend is followed in 4D and 5D transition series. Difference in 5D and 4D transition series atomic size is less due to lanthanoid contraction. Shielding of one 4f electron by another is less than that of one d electrons by another, and as in nuclear charge increases along the series, there is fairly regular decrease in the size of entire 4f orbital. The decrease in metallic radius coupled with increase in atomic mass results in general increase in density of these elements. So from titanium to copper, the significant increase in density may be noted.